Hi everyone. Today we're going to be looking at 12C Part 3, continuing our work on transition matrices. Today we're going to be looking at using recursion to work with transition matrices to generate state matrices in a step-by-step approach and then using a rule. So what I'm going to do is I'm going to go ahead and share the notes that I've provided for you for Chapter 12. And I'll talk to the notes rather than trying to do everything on the whiteboard. So we've used recursion before in further maths. We did it in the topic of recursion and financial modeling, and it was used to generate more information, basically. So we had some starting information. We might have had the principal or the starting balance of a loan or an investment, and we used recursion to try and figure out or predict what's going to happen after a certain period of time. So whether it was simple interest or compound interest, whether it was a reducing balance loan or an annuity, we looked at different situations where recursion could be used, and it was all about generating more information for us. And the calculator was very useful in doing that, and it will be again this time. So it goes back to the recursion type formulas that we saw in that module. However, this time we're going to be using matrices in addition to recursion. So it's a little bit different, but hopefully you pick up some similarities to what we've already done. So we're going to return to the car rental problem. So this has been a situation that we've used all through 12C, exercise 12C. We've got the rental firm with two branches, one in Bendigo and one in Colac. And the car rental firm is now planning to buy 90 new cars. Okay, so they're going to put 50 of them in Bendigo and 40 in Colac. And what they want to know is if we start off with the 90 cars balanced out in that way, 50 in Bendigo and 40 in Colac, how many cars will be at each location after 1 week and then after 2 weeks and so on. Okay, so what we can do is use a matrix recurrence relation to predict how many cars will be located or available for rent at each town from 1 week to the next. And the recurrence relation uses what's called an initial state matrix and the transition matrix. So a state, what we're talking about in terms of a state in this problem is where is the time frame? Is it the initially, or is it after 1 week? Is it after 2 weeks? So a new state in this type of problem is basically a new week. So we're trying to work out where the cars are located from 1 week to the next. Now, initially, we know that there are 50 in Bendigo and 40 in Colac. Now, it's important that we can construct an initial state matrix, which is called S0. Now, we looked at V0 many times in recursion and financial modeling. S is obviously used because it's a state matrix. The naught indicates that it's the initial state matrix. So it's at like week 0 when the cars are bought for the first time. So make sure that we always include rows and columns in the same order. So if I'm putting Bendigo and Colac in alphabetical order, then the 50 would go at the top for Bendigo and the 40 would go underneath for Colac. And my transition matrix, when I construct that, okay, this is the same transition matrix we've used before, must follow that same pattern. B, then C for the columns, B, then C for the rows. Remember that we had 80% of cars rented in Bendigo were returned to Bendigo, whereas 20% of cars rented in Bendigo were returned to Colac. 10% of cars that were rented in Colac are returned to Bendigo, and 90% of cars that were rented in Colac are returned to Colac. So the textbook often leaves out the from and the to, and they've also left out the column and row headings, but I definitely suggest and encourage you to put them in B, C, B, C, from at the top, to at the side. Okay, so what we can do is we can generate the number of cars in Bendigo and Colac after 1 week by multiplying our transition matrix by our initial state matrix. So our transition matrix multiplied by our initial state matrix. Here are the calculations. Remember, we split our first matrix up into rows and our second one into columns, and we get these multiplications and additions, and we end up with 44 and 46. Now, this matrix here, we're going to call S1. So this is our state matrix after 1 week. Okay, the top number refers to the cars in Bendigo, the bottom number refers to the cars in Colac. Now, one thing to recognize is that these numbers still add up to 90 because all the cars went somewhere. All the cars that were in Bendigo either returned to Bendigo or went to Colac, and all the cars that were in Colac either returned to Colac or went to Bendigo. So no car has been lost or misplaced, and we haven't ordered in any new cars. We've still got the 90 cars that we started with. Okay, and that's going to be a consistent pattern that we see, no matter whether it's S1 or S2, which is the cars after 2 weeks, or S3, which is after 3 weeks. The numbers in our state matrix will always add up to 90. Okay, so if we try and work out where the cars are after 2 weeks, we do T times S1. So I'm transitioning from state 1 to state 2 now. So T times S1, I pre-multiply by transition matrix T, and you can see that this second matrix in the multiplication is now my numbers from S1, okay? When I perform the multiplication, we end up with 39.8 cars in Bendigo and 50.2 cars in Colac. Now, obviously, you can't have 39.8 cars and 50.2 cars. So what I suggest you do if we had to work out the number of cars in each venue after 2 weeks is show this working out, show that S2 is 39.8 and 50.2. So express S2 to 1 decimal place. Then in a worded answer, round off to the nearest whole number. So my worded answer would be after 2 weeks, we predict that there will be 40 cars in Bendigo and 50 cars in Colac, right? That's different to what we started in. We started with 50 in Bendigo and 40 in Colac, and they've actually swapped over. So we've now got fewer cars in Bendigo and more cars in Colac, 40 and 50, okay? Then we can work out S3. So this time I take my numbers from S2 and I keep my unrounded answers, 39.8 and 50.2. Just because I wrote a worded answer with whole numbers, I certainly keep 39.8 and 50.2 in my calculator when I do the next calculation to get S3. And my S3 numbers turn out to be 36.9 for Bendigo and 53.1 for Colac. So the way that the 90 cars are divided between the two locations is changing all the time. That's why these are called transition matrices, transition, change. All right, so after 3 weeks, we predict that there will be approximately 37 cars in Bendigo and 53 cars in Colac. Okay, so you can see the pattern that we're getting. S1 is T times S0, S2 is T times S1, S3 is T times S2. And we can continue the pattern to work out where the cars are located in week 4 and after week 5. This is our general recursion formula. We've seen these before. The next state, Sn plus 1, is equal to our transition matrix times our current state, Sn. Okay, so just like we had recurrence relations in our finance section of the course, we've now got recurrence relations for transition matrices. S0 is the initial state or the initial value. This is usually going to be a 2x1 matrix, but it could be a 3x1 matrix. And Sn plus 1 equals T times Sn is the rule that we've got for our recursion model. Okay. There's another example here where we had a factory with a large number of machines. The machines are either operating or broken. At the start, we've got 80 operational machines and 20 broken machines. Notice that there are 100 machines overall. So using the recurrence relation, we've got our initial state that we start with, and then to work out the next state, we always multiply the transition matrix by our current state. So in the calculator, we would store our initial state and our transition matrix. In fact, I'm going to do that right now. So 80 and 20 is my initial state. So on a calculator page, you know that we can press the templates button. Our initial state matrix is a 2x1, so I choose that option. And we had 80 operational and 20 broken machines. I'm going to store that as S0, S0. Okay, once I've done that, I'm going to store my transition matrix as capital T or as lowercase t in the calculator. So 0.85, 0.15. This is a 2 by 2 matrix, so I choose that option. 0.85 and 0.15 in the first column. And in the second column, we've got 0.05 and 0.95. I'm going to store this as matrix T. So if I want to work out what S1 is, let's just refer to the questions. Each day is going to be like a new situation here, a new state. So we want to work out the number of operational and broken machines after 1 day and then again after 3 days. So after 1 day, to work out S1, I would be doing T times S0. And now that I've defined them, I can just do T times S0. They should be bolded because the calculator recognizes them. And that's what we get for the machines after 1 day. There will be 69 operational machines and 31 broken machines. Okay, remember that operational machines are the top number always, and the broken machines are the bottom number always. Okay, so the reason that this is happening is if you notice these two percentages, the 0.15, this is 15% of machines that were operational are now broken, and only 5% of machines that were broken are now operational. In other words, this factory is finding that there are more machines broken in a day that were operational to start with than vice versa. So they're breaking more machines than they're fixing, which is probably not a good thing. So that's why after 1 day, compared to the initial breakdown, we've now got fewer operational machines and more broken machines, okay, as we can see on the calculator. Now, I want to work out what S3 is, okay? This was S1. We want to work out the number of operational and broken machines after 3 days. So what I can do is I can actually take this matrix and store it as S1, okay? Now the calculator recognizes this as S1. Now, if I want to find out what S2 is, I do T times S1. Okay, so this is the next day now. This is 60.2 machines are operating and 39.8 machines are broken. So again, this is S2. I want to get to S3. So I can just copy this matrix down and call it S2, store it as S2, because that's the values after 2 days. And now to work out the values after 3 days, I do T times S2. This is the values after 3 days. So after 3 days, there will be approximately 53 machines operating and 47 machines that are broken. Okay, so you can see there's my S2 and there's my S3. Okay, so round off in your worded answer to whole numbers, but in your matrices, when you're showing the calculations, keep the unrounded versions with the decimal places shown. Okay, so there's our bit of a diagram in the notes for the calculator. All right, now we're going to look at a rule for determining the state matrix of a system after n steps. Imagine we wanted to know how many machines were operating and how many were broken after 15 days. Well, I don't want to have to repeat that process 15 times. So what I'm going to do, I'm going to show you on the board a bit of a diagram that will hopefully help to explain this. We've seen similar diagrams in recursion and finance. Okay, hopefully you can see this. T is my transition matrix. S0 is my initial state matrix. So you can see that I can go from S0 to S1 to S2 and then to S3 step by step using my recurrence relation. We've just done that in that example. In each case, we pre-multiply by T. So if I want to get from S0 to S1, I do T times S0 and that will get me S1. To get from S1 to S2, T times S1 gives me S2 and so on. Now, let's say that I want to jump from S0 all the way to S3. Then what we can do is instead of pre-multiplying one at a time, I can pre-multiply by T to the power of 3, because is this like time T times T times T? And T times T times T is T to the power of 3. This is similar to what we did when we were working out our rules for geometric growth. We're pre-multiplying by t to the power of 3. So S3 can be worked out really quickly by doing t to the power of 3 times my initial state matrix. And then I can apply that for any state that I want to find, Sn, by my rule being t to the power of n times my initial state matrix S0. Okay, so if I wanted to work out the value of S30, I can do t to the power of 30 times S0, and I'll get the answer really, really quickly using the calculator, of course. So if I go back to the notes, remember in that previous question, we wanted to work out how many machines were operational and broken after 3 days. So I did it recursively, step by step, working out 1 day, then 2 days, then 3 days. But if I store S0 and T in the calculator, which I already did, remember that if I ask the calculator what was S0, it tells me the initial breakdown, and T, it tells me the transition matrix. Well, S3 is going to be T to the power of 3 times S0, and I get my final answer. Remember 53.16, there it is up there, and 46.84, but now I get it in one step using the rule, okay, because I've used the power of 3. That tells me I'm 3 days further along from my starting day, okay? So that's how the this rule works. It's really, really handy. The diagram here I've got in your notes is just the diagram that I had on the board, okay? And here you go. We can see how many machines are operational and broken after 10 days. Same transition matrix, same initial state matrix, and I can just do t to the power of n. Sorry, t to the power of 10 times S0. And this tells me the breakdowns after 10 days. So now there'll be only 30.9 machines that are operating and 69.1 machines that are broken. So rounding off as a worded answer, I would say 31 operational and 69 that are broken. Okay. Last thing for 12C part 3 is what we call a steady state solution. So what's going to happen is over time, let's go back to the problem with cars in where were we? Bendigo and Colac. So we started off with 50 cars in Bendigo and 40 in Colac, and we saw that after 1 week, there were fewer cars in Bendigo and more cars in Colac, and then after 2 weeks, and then after 3 weeks, the numbers are changing all the time. And you might wonder, is this pattern going to continue, or are the numbers going to continue to change, or at some stage are they going to become fixed? And the answer is, anytime we've got these transition matrix problems, we end up reaching what's called a steady state or an equilibrium state solution. Steady state or equilibrium state means unchanged. So eventually, the number of cars at each location from week to week will remain unchanged. There will still be some cars going across from one to the other. However, the number of cars that move from Bendigo to Colac will be exactly the same as the number of cars that go from Colac to Bendigo. We're not going to reach this steady state until a number of weeks or months or years down the track, but we do eventually reach this steady state solution, okay? What you can see is that after a total of 15 weeks, we've reached steady state because the number from week 14 to week 15 are the same. 30.1 cars in Bendigo, 59.9 cars in Colac. Even from week 12 to week 13, there was not a lot of change, but the numbers were slightly different. And from week 13 to week 14, the numbers were slightly different. But from week 14 to week 15 to 1 decimal place, the numbers have remained the same. That's an indication that we have reached steady state or equilibrium state, okay? You can see what's happened here. If we plot the number of cars at each location over time, the number of weeks is on our horizontal axis and the number of cars is on our vertical axis. You can see that we started off with more in Bendigo compared to Colac, but over time, first of all, they swapped places. So after a little while, there were suddenly more cars in Colac compared to Bendigo. And you can see that these curves are flattening out and eventually they become horizontal. Okay, so the number of cars in Colac remains fixed at 60 and the number of cars in Bendigo remains fixed at 30. And no matter how long I continue this graph for, those curves are going to remain horizontal. Okay, so in a steady state, as I mentioned, cars are still moving between Bendigo and Colac, but the number of cars going from Bendigo to Colac is exactly balanced by the number of cars going from Colac to Bendigo each week. And that's why we've reached steady state. For a system to have a steady state, the transition matrix must be regular. So there are no zeros in our transition matrix. I should make that point. And the columns have to add up to 1, as a transition matrix always does. Okay. Now, really importantly, how do we determine when steady state has arrived, or how do we do our calculations? Well, normally we will have reached steady state by the time that we're at 50 or 51 states down the track. So S50 and S51, normally there will be no change. So what we do is we use our calculator to determine the matrix for S50 and use our calculator to determine the matrix for S51. And if we can show that those matrices S50 and S51 are identical, then we've reached the steady state. So here is an example. Determine the steady state solution for the car rental problem by calculating S50 and S51 and write down the number of cars based in Bendigo and Colac in the long term. That means after we've reached steady state. So I'm putting S0 and T into my calculator. I'm going to do that now. So we started out with 50 in Bendigo and 40 in Colac. That was my S0. Great. Just make sure that was right. Yep. And our transition matrix was a 2 by 2. We had 0.8 and 0.2, and then 0.1 and 0.9, and that was stored as matrix T. Okay, good. So let's check what the values are for S50. Remember, to get S50 using our rule, we do T to the power of 50 times S0. And that's what we get for the number of cars in Bendigo and Colac, so basically rounding to 30 and 60. And if we do T to the power of 51, so they've got to be consecutive. I've got to do 2 states that are next to each other, okay, 50 and 51. I could do 80 and 81 or 100 and 101. That would be fine. And you can see that by this stage, to the first 5 or 6 decimal places, my answers are completely the same. All right, 30.0000, 59.99999, and the same for this one. Okay, so this indicates that we've reached steady state. How would I describe this in my answers? I would need to, in my working out, show that S50 looks like this and show that S51 looks like this. So I would include that in my working, and then I would state that in the long term, or after steady state, 30 cars will be based in Bendigo and 60 cars will be based in Colac. Okay, so that's how we interpret a steady state problem. Might very quickly look at the textbook for 12C part 3 and see if there is a question asking about steady state. These are pretty long questions. Let's look at this question 5, just because it's a 3 by 3. So I will just do one more question. I know this video has been a bit longer, but in another model of this world, people can be happy or neither happy nor sad or sad. The way people feel can change from day to day. We understand that. The transition matrix opposite shows how people's feelings may vary from day to day in this world. I don't know what world they're talking about, but I don't know. Whatever world. And the proportions of people involved. So this is our transition matrix. The columns always add up to 1. We're going from and to. So from happy to happy, 80% of people who were happy one day will remain happy the next day. 15% of people who were happy one day will become neither happy nor sad the next day, and 5% will become sad, and so on. We might focus on parts C and D, right? And I'm going to do this on the calculator. So I'm going to store my transition matrix first of all. So 0.8, 0.15, and this is a 3x3 matrix, 3x3, 0.8, 0.15, and 0.05. Then we'll have 0.4, 0.3, 0.3. Notice that the calculator won't, oh yeah, it will do, sorry, 2 decimals. So I should stick with that rule of doing 2 decimals. 0.30, 0.30. And lastly, the third column, 0.35, 0.4, and 0.25. 0.35, 0.4, and 0.25. I'm going to store that as matrix T. I've got a feeling that they will eventually revert back to 1 decimal place. Yeah, they do, but we've entered that correctly. All right, our initial state was oops, that's the wrong thing. We initially had 2,000 people, or we've still got 2,000 people. They've been defined initially as 1,200 being happy, 600 neither happy nor sad, and 200 are sad. So my initial state matrix is a 3x1 matrix this time, because there are 3 different categories. And we had, what was it? 1,200, 600, and 200. For this as S0. Okay, I'm not going to do all parts of this question, but if we look at after 5 days, how many people do we expect to be happy? Then because this is after 5 days, I don't want to do it step by step. I want to do t to the power of 5 times S0. Okay, now remembering that our order was happy, then neither happy nor sad, then sad, that order remains fixed. So we've got 1,310 people are expected to be happy after day 5. Okay, we'll just write down the correct matrix to, let's say, 1 or 2 decimal places. So 1310.33, 429.82, 259.85. But then my worded answer would round to the nearest whole number because it's people. 1,310 people are expected to be happy after 5 days. The last part of this question, in the long term, how many of the 2,000 people do we expect to be happy? So in the long term means I'm comparing 2 successive states with big numbers, like t to the power of S50 is going to be this breakdown of happy, neither happy nor sad, and sad. And I'll do the same for t to the power of 51 times S0. And you can see that to at least, to all those decimal places, the numbers are identical, okay? So in the long term, we're going to expect 1,312 people to be happy, 429 people to be neither happy nor sad, and 259 people to be sad based on this transition matrix. If I was to try and get steady state and I did t to the power of 12 times S0 and t to the power of 13 times S0, oops, typed that in incorrectly. Yep, I've got to move the cursor down, times S0. Notice that we haven't quite reached steady state. I guess to 1 decimal place, the numbers are the same, but you can see to 3 decimal places, 737, 739, there's still a little bit of variation. So that's why we choose big numbers like 50 and 51. Usually we can be pretty sure that we've reached steady state by the time we get to 50 and 51. Okay, that's it for 12C part 3. One more video to come on 12C part 4, which I'll put up shortly. Thank you very much. See you later.